Okay, welcome to lecture number 7. Today what we are going to do is we are going to plot these free electron band diagrams on an empty lattice. What that means I will explain in a minute, but let us recall what we did. Let us see what we are trying to do. What we are trying to do is, we know that energy is equal to h square by 2m k square. That is the free electron energy. So, if I want to plot this, then I can simply take E and K and plot it, but then problem, remember, was that K is a vector. So, what direction should I choose? Because once I am plotting E versus K, then what direction does K represent? That is question number 1. Question number 2 was K, of course, its extent is from minus infinity to plus infinity. Now, how do I plot it therefore? So now we have a trick. Now, remember what we did was we derived equation for energy in free electrons without any regard to the underlying lattice. Then we introduced that if there is a lattice, there is a periodicity in the lattice. Fine. Now, what is the consequence? Then next step we did was that if there is going to be any periodic potential, though energy of free electrons was derived with potential equal to 0. So, yes, we will have to correct for that also eventually, that energies also have to be calculated correctly, but for time being, if you assume that energy indeed varies as E versus K square, then we will continue to call it as free electron band diagram. That is just an assumption, temporary assumption, but then in reality, since there is a periodic potential in the lattice, which I will show in the next lecture one more time, but since you can clearly see, since we got periodic lattice, so the potential also, there is a potential also which will be periodic, and as a consequence of that, there is a Bloch theorem which allows us to make certain conclusion, and that helps us in plotting band diagram. That is my purpose of today's lecture, that if I have a lattice, there is a periodic potential, though energies have been calculated with 0 potential, we will just use those as numbers on the E scale, but on the K scale we will use what we learn from if the potential was periodic. What did we see? That if potential was periodic in R, where had a period of capital R, in that case we had shown, I had shown that it is always possible that if you have a vector K, then it is always possible to write it as a vector K prime plus some reciprocal lattice vector, such that this K prime is in first Brillouin zone. It is in first Brillouin zone. We can always find a capital K vector such that this K prime vector comes in first Brillouin zone. So, now this is one thing I had shown you geometrically. Second thing I had shown you was in the previous lecture that there is no unique K which defines the wave function, namely phi of K at R plus R is simply equal to e to power j k dot R phi R, or I could also write it as phi K prime R plus R equal to e to power j K prime vector dot R phi of R. So, now you can see that it does not matter whether you choose K or K prime, it is the same thing as long as K and K prime are different from each other by a reciprocal lattice vector here. So, this is the trick. So, now you see, instead of, while this, since it does not matter to us what actual K is, I can always find a K prime whose limits are only within the first Brillouin zone, and hence I do not need to plot EK diagram all the way to infinity. I can plot it only up to K prime, and when I plot it, then I mark it out that what capital K I have used in order to do this transformation. Keeping track of it, I can always calculate energy as E h square by 2m. That means if I know K prime and I know what K I have used to get to a K, then since my energy is K square, that is equal to h square by 2m K prime plus K vector. Let us write explicitly K prime plus, let us write the square like this. So, that is the same thing. So, if I know a K prime, so instead of plotting E versus K, I will plot E versus K prime whose limits are only within first Brillouin zone. When I plot, so I will also write what K I am going to use so that in case you want to calculate the energy, you can simply add the k to k prime, calculate small k and take square of it to calculate energy. All right. So, that as an example, let me show you as an example. Let us consider a one dimensional lattice. What does that mean? Let us say that my lattice, to make it simple, to keep it simple initially to understand what we are trying to do, let us assume that lattice is one dimensional and then eventually I will go to three dimensional real lattices. So, let us say this is what I mean. Let us say it is a one dimensional lattice with a lattice parameter of A. So, this is the lattice parameter A. If we consider this to be the origin and this is x direction, if we consider this as x direction, then I will define my lattice vector. What is the lattice vector for this then? In that case, I can write this lattice vector as some n times a lattice vector, which is same thing as n times a x hat, meaning thereby a vector is simply equal to, the lattice vector is simply equal to a x hat. So, a is the periodicity of this. If so, let us now find the reciprocal lattice vector. Reciprocal lattice vector, of course, now has condition that we find a reciprocal lattice vector such that e to power j k dot r should be equal to 1. If that is the case, and if I define my k to be equal to some m times b vector, in that case you can clearly see that if I substitute r and k in there, then what would I find? I will find k must behave as equal to something, as equal to, or maybe I use not m, but I use, let us for time be, or let me use. So, if I substitute in there, what does that tell you? That says that I should have k, which is k vector should be simply equal to 2 pi by a x hat is what this k should be, implying that b should be equal to or k should be equal to m times, I should say, m multiples of it, where b being this quantity here, this quantity being b. So, that is what this quantity should be equal to. So, you can see that if I substitute r and k, I will get e to power j k dot r as 1 if I choose my reciprocal lattice vector as like this. What does that mean? Even in reciprocal lattice, the lattice is one dimensional, and in that case if I plot it again, the reciprocal lattice, then reciprocal lattice looks something like this, again one dimensional with a periodicity of 2 pi by a. Now 2 pi by a is the periodicity of the reciprocal lattice. So, if I am looking for the Brillouin zone, remember what do we do? What we do is, so this is x equal to 0, let us say x equal to 0, then in that case what do? We take perpendicular bisectors to these lattice vectors. Here is a lattice vector for m equal to 1, and here is the lattice vector for m equal to minus 1, and if I take perpendicular bisectors to it, here is the perpendicular bisectors, then this is my first Brillouin zone. Same construct in one dimension. In 3 dimension, these bisectors were planes. In 2D, which I had shown you earlier, these bisectors were lines. In 1D, these bisectors are simply just these points. I should use a different color here because this is not a lattice point. So, I should use this, and here is the bisector points are right here. These are bisector points, and this is therefore pi by a, and this is minus pi by a, since the lattice parameter is 2 pi by a. So, now notice that now what that means is that if I want to plot E versus k diagram, let us say E now varies as h square k square by 2m. Now, of course, problem is straightforward, since k is only in one direction. So, I can always plot E versus k like this. I can take E versus k, and let us say this is k, which is simply x direction essentially, or k x direction if you wish. then in that case I can simply plot the parabola E versus k square like this. I can calculate, and this is the energy. So I can calculate E versus k as a parabola. Fine, that's because only one direction. But what I want to show you by in this one dimensional case is that we need not plot this parabola all the way to plus infinity and minus infinity. We can, if this is 0, and we can think of two lines here, which is at pi by a, first Brillouin zone, minus pi by a, and we can represent all this information by plotting this curve only within these two limits. Only within these two limits we can plot, and we can show this entire diagram in these limits only. I want to show this to you for one dimensional case, and then move on to 3 dimension, where we will use this fact and plot it out for 3 dimensions. So let's do that part and show it to you how this will be done. So here I am going to label this for you. There's something what you need to show, what you need to see is only the portions I keep labeling. So here is the energy that I am plotting, and this is k. This is k which I am plotting, which I am trying to plot, and in this here is 0, here is 0, here is the lattice point right here, another lattice point is right here, therefore it is 2 pi by a lattice point here, periodicity is 2 pi by a in reciprocal lattice, so 2 pi by a minus, then therefore this is 4 pi by a, another lattice point, and here is another lattice point which is 4 pi by a, that is the lattice point. Now if I plot E versus k diagram, then I can simply plot this as this line which you see as a blue line right here. Here is the parabola E versus k square. I am plotting this blue line, shows a plot of E versus essentially h square by 2m k square. That is what basically this parabola has been plotted as. This is what I have plotted out. Now what I am showing you is I have drawn 2 lines right here. The 2 lines I am plotting, this line and this line I am plotting, and here is my pi by a, and here is my minus pi by a. Here is my minus pi by a. This is my first Brillouin zone. My first Brillouin zone, which I showed you in just a second ago. Now this is my first Brillouin zone, and I want to show you that everything can be plotted in here. Okay, if that is the case, let's think of another axis. What we can think is like this, that we will think of another axis running from here, this is 0, and whose extended only up to here, and this is my k prime axis. Here is my k prime axis. So there is the axis running from here to here, which is k axis, and there is the axis running from 0 to pi by a, or 0 to minus pi by a, that is the limit, and that is k prime, because remember k prime is a vector which belongs only in the first Brillouin zone. Why so? Because k and k prime are always related by capital K. So let us substitute this out. So then therefore any vector k will be equal to a small vector k prime plus some m times 2 pi by a x hat. And remember k and k, I am going to drop this vector and sign in there because everything is in x direction. So this k is also in x direction, and this k prime is also in x direction. Everything is in x direction. Now so when m is equal to 0, so let us use this blue line and I will darken it. When let us say m is equal to 0, then I will double this line, thicken this line here, from here to here I am going to plot it. This is for m is equal to 0. Here is m equal to 0. For m equal to 0, k is equal to k prime, and I am going to plot k prime versus energy. So that is simply, I am going up to this point. Now if I go and for the points beyond this, that means let us say I am looking for these points right here up to here, from here to here. Let us use another color, let us use a red line. Let us say I have a line which is like this. Here is the red line which runs like this continuing line is the red one, and use another color. Let us use green color, which is this portion of the line curve. Remember, I am saying these red and green portions now also have to be plotted in first Brillouin zone. So, what can we do? What we can do is that suppose you now use m is equal to +1 and m equal to -1. If you use that, what happens? Let us use m equal to +1 for a minute. If m is for m equal to 1, what happens? Then k is equal to k prime plus 2 pi by a, which means k prime, so you notice that if I use this lattice point, this k vector, the m equal to 1 means what? M equal to 1 means that the capital K vector I am using is this vector from here to here, next lattice vector. This is the lattice vector k, equal to 2 pi by a. That is the lattice vector I am using, capital K reciprocal lattice vector. If I use this lattice vector, any k value here or here, any of these k values can now be transformed into a k prime which belongs to first Brillouin zone by using this capital K. If so, then if this is the value of k, if say let us say this is the value of k right here, if this is the value of k, then what is the value of k prime? So, if this is the value of k, I can substitute that value of k in there and calculate k prime as k minus 2 pi by a. Essentially, now if I calculate this, if I use this, so I find a k prime by from whatever the k value is. If this is the k value, if this is the k value, from this k value I subtract out 2 pi by a, then I am basically back in, I will be back in essentially this whole curve, then red curve can be represented in here like this. This red curve therefore shifts from this point, therefore shifts to this point by capital K vector, and this point shifts to this point by capital K vector. By capital K vector we can shift these 2 points. Similarly, for green line, this green line will shift same energy remains the same, but can be plotted by shifting this point like this and this point over to here. Essentially, what we have done is that used minus m equal to -1 or m equal to 1 to transform all points into the same segment of the parabola, which is shown here, right here, this segment of the parabola, into the first Brillouin zone by doing this. And I have shown you 2 green segment for m equal to -1, then k prime would be equal to k plus 2 pi by a, which is essentially a parabola which is centered at minus 2 pi by a. That is the parabola which is centered at minus pi by a. So, essentially you can see that whatever value you take, if you subtract from that this k value, subtract 2 pi by a, all the red points get shifted into the first Brillouin zone. If you take all these green points here, add to it 2 pi by a, you add 2 pi by a to it, and then you can see that that can be shifted into it can be shifted into this can be shifted into back into this within the first Brillouin zone. This green curve also can be shifted into the next Brillouin zone. Now, if I look at further another portion of it, let us say we look at this portion of here going up to further up. This portion, if I see, now I can use 2k vector, and this portion can again be transformed into, now I can again transform it into this particular curve, and then this will be transferred as follows. Where this is equal to 2k, two times 2 pi by a, and similarly this portion of curve, let us use another color, this portion of the curve which you see here can be transformed right here by the same way. I can shift this quantity right here from here using 2 times 2 pi by a. So, this curve is for m equal to 2, and this is for m equal to minus 2. So, you can see that every portion of this parabola in this form we can keep shifting to, we can keep shifting this into the first Brillouin zone. Essentially, therefore, if I now read as follows, if I take a value of k prime, if I take the k prime to be, let us say, this value, and I read m equal to 0 right here, m equal to 0, then all I need to do is take the square of k prime and I can get this energy which I just plotted out here. Right here, if I want to take this k equal to this point, k prime is this point which I am showing you here, and if I use m equal to minus 1, then it simply means that is k prime is equal to k prime k minus, if I use my k 2 pi by a. Therefore, so at this point I can keep calculating k values, which is k prime is right marked here. This is k prime I am talking about, this is the value of k prime, and since I am reading this green curve m equal to minus 1, so then that means it should be equal to minus 2 pi by a. I can take square of this and calculate the energy still as E h square by 2m k square now, and I will find this energy to be equal to this point. Similarly, if for same k prime I took m equal to 1, then in that case, in that second case, the which I am now describing, m equal to, in this case, minus 1, for m equal to 1, I would write then k, and I will use this k prime, here is the k prime value here, plus 2 pi by a, and in that case again energy will be calculated in the same way, and I will calculate the energy to be here. And if I use similarly m equal to minus 2, then right here, if I use m equal to plus 2, then I will be right here in these 4 points, and this way for all the entire this parabola, this whole parabola which is going all the way up to infinity, can be represented only within the confines of first Brillouin zone by using these lines, different lines within the first Brillouin zone, and labeling them appropriately with the value of m. If you introduce in there, then you can see that we can basically confine this entire thing, this entire band diagram. Essentially, what we need to do is confine this whole thing only within this region. Only within this region we can look at it, and this is the band diagram really. So now you can see that x axis is confined because of Bloch's theorem. Though energy we are still using as the free electron energy, which energy values may be incorrect, but I am just merely trying to show you that x axis is not limited. X axis can be limited to the extent only within the first Brillouin zones. All k points can, since they can be collapsed back into the Brillouin zone, therefore we can represent them into first Brillouin zone essentially by plotting E versus k prime, whose extent is from minus pi by a to pi by a with 0 in between. And not only that, you can see, since it is symmetric about k equal to 0, therefore you need to plot within the first Brillouin zone only 1/2 of it. That should be adequate. That means, in fact, if you plot only this half from here to here, that should be adequate enough to represent the band diagram, because we know the other side is simply the mirror image of it. So therefore, that should be simply sufficient. So now you can see, actually you can plot this band diagram only within the half of the Brillouin zone. Alright, so this is a general idea how do we represent a band diagram in a confined space, and why we are trying to do this, because in this case it is only one dimension involved. When there are multiple dimensions involved, what do we do? So let us move on to this three dimensional now real systems and try to show you how band diagram using this principle constructed in that case. So with that, then we will be able to understand how band diagrams are done. So in order to do so, let's use this. Let's use FCC. So now three dimensional. Let's do the 3D now. Let's consider FCC. If you look at FCC, then what happens in the case of FCC? FCC lattices, reciprocal lattice vectors for FCC are given right here, 2 pi by a y hat plus z hat minus x hat, and then 2 pi by a z hat plus x hat minus y hat right here, B2, B3, 2 pi by a x hat plus y hat minus z hat right here. And how does this look like? FCC reciprocal lattice looks like a BCC. So what is a BCC? So what I have shown you here in this picture is, here are the lattice points, BCC lattice points, here are the BCC lattice points in one cell, and this lattice parameter is 4 pi by a. Recall, reciprocal lattice for FCC has a lattice parameter is BCC and its lattice parameter is 4 pi by a. So here is 4 pi by a, and then there is a lattice point right in the center. About that, then you take perpendicular, take this at right here like this, construct like this, take perpendicular bisectors. Here is the perpendicular bisector. You go, there is another lattice point right here for another cell I have shown you. Here is a line running like this from to here, and this is the perpendicular bisector for it. Right here is where it intersects. So using that, we have constructed this Brillouin zone. So this is a Brillouin zone. This Brillouin zone is now shown separately right here also, and I had told you that there are some, the center point is called the gamma point, and then a vector b1, this vector b1 vector is shown right here. B1, remember, is and this whole distance is lattice parameter 4 pi by a, again remember that. So this is 4 pi by a, 4 pi by a. So that is the lattice parameter. Once this is the lattice parameter, then you can see that I have taken x direction. Here is the k x direction, here is k y direction, here is k z direction. So this is z direction. If these are the x, y and z directions, then you can see b1 vector, you can see the b1 vector, the b2 vector, the b3 vector, which is corresponding to this, which is move in y direction. Let us do one of them. So b1 vector, if you want to do in y direction, move half, in z direction move half, and in minus x direction move half. So let us move in from the center point right here. Let us move half in y direction, so we reach here. Let us move in z direction half, we reach here, and let us move to minus x direction a half, then we reach here. So that is from gamma point to this point right here is therefore the b2 vector. This gamma point of course is just 0 0 0, that is the center of this. Using this as a reference, let us look at x point. X point is right here, x point is shown right here. So what is x point? This x point therefore is simply 2 pi by a x hat. 4 pi by a is the lattice parameter. So x point, this point, coordinates of this point are 2 pi by a x hat and 0 0 in y and z direction of course. So whatever is not written x hat is 0 point. So that is the vector here. From gamma to x, this is the vector. And if I look at w point, remember x point is not one point, even this point is x point of same symmetry, even this point is x point. So I have written it in x direction, but x vector could also be 2 pi by a, in fact plus minus I can put, I have taken plus 1, but I can take minus 1 also. You can take plus minus 2 pi by a, you can take 2 pi by a y hat, or you can take plus minus 2 pi by a z hat. All these are x points. So I have shown you only one, but they all are equivalent symmetry, so they are all considered x point. Similarly, look at w point, which is right here. So these w points are equivalent symmetry everywhere. So this is also a w point, this is also a w point, etc., etc. So these are equivalent points. I have shown you the one which is marked here. This particular point I have shown you. This particular point is therefore 2 pi by a x plus half y x hat plus y half y hat. Try it out yourself. Then the L point, I have marked out this point, this is also L point, this is also, so all these are L points, these are all L points, and I write here the one I have marked here, I am writing that particular one, but all are equivalent points. So those are 2 pi by a, half in x direction, half in y direction, and half in z direction. So that's what this L is. Similarly, k point I have marked out. I have marked out this k point, but whatever hexagons you are seeing there, midpoints of those all are equivalent points, and they all, therefore there will be well, k point and a u point is also marked here. So all k points of equivalent symmetry, that means this will be a k point, this will be a k point right here. All these three will be k point, and the other ones will be where a 4-sided figure joins the 6-sided figure, those will be all u points. So that means this will be a u point and this will be a u point, and so on. So that's, you get the idea. What we're going to do is now plot these band diagrams within certain direction, some particular direction. For example, if you think that k prime will allow k prime to go from gamma to x. So I want to plot a band diagram, energy versus some k prime is what essentially I am going to plot, and k prime I will confine in the first Brillouin zone from gamma to x. Remember, gamma is the center point and x is the edge of the Brillouin zone. So I am going to plot from gamma to x, and whatever it is, mirror images in minus x direction also. So therefore we don't need not plot that. So if I take this, then I can plot these energies for this k prime. So I can take any k prime. So let us say this is k prime right here. This is this value of k prime, which is equal to, let's say, half the distance between gamma and x. So let's plot that out. Now how would we plot this? So once I know k prime, remember I can always find a k which is k prime plus some capital K prime plus capital K vector. Now what is the capital K vector in this case? That capital K vector is m1 b1 plus m2 b2 plus m3 b3. So what is this K vector? Let's expand it out by substituting b1, b2 and b3 from right here. If you substitute in there, what do you get for FCC? You get this as 2 pi by a. So let's substitute in there value of b1 in there, b2 in there, and b3 vectors in there. So that k then becomes minus m1 plus m2 plus m3 x vector m1 minus m2 plus m3 y vector plus m1 plus m2 minus m3 z hat. So that's the k vector. So now, and what is k prime vector? For this particular k prime vector, what is it in from gamma to x direction? This k prime vector, I can write it as something alpha times 2 pi by a x hat. I can write it like this, where alpha goes from 0 to 1. Alpha goes from 0 to 1. That means when alpha is 0, then I am at gamma point. When alpha is equal to 1, then I am at x point. Then I reach this x point. All right. If I do so, then an alpha takes a value from 0 to 1. So if I substitute that k prime also in there, then in that case k simply becomes equal to 2 pi by a. So I am going to substitute this k prime in here, and I am going to take this k which I have just written out, and I am going to substitute that right in here, and I calculate k. In that case, k is equal to 2 pi by a alpha minus m1 plus m2 plus m3 x hat plus m1 minus m2 plus m3 y hat plus m1 plus m2 plus m3 z hat. And now you see I can calculate, I can substitute different values of m1, m2 and m3 in this expression and calculate energy as h square 2m and k square, a free electron energy I can calculate. Okay, so energy, then once I calculate this A, for different values of m1, m2, m3, and remember alpha only varies from 0 to 1. That means I will always be confined within the first Brillouin zone in direction of gamma to x point. So, as long as I am confined between these 2 points, that is where I am going to plot. I am going to take a k prime value. That k prime value is defined by alpha. If I take a alpha value whatever 0 or 1, accordingly k prime value gets fixed, and I use different m1, m2 and m3, and I can now plot out all different energies with this index m1, m2, m3, just like in one dimensional case we used 0, 1, minus 1, 2 and minus 2. Here, since it is 3 dimensional case, I will have to use 3 indexes m1, m2, m3 to label different segments. Now, I have done this calculations for you. So, let me first show you these calculations which I have done for you, and so that you will see. Here is the gamma point, here is the point, this is the gamma point right here, this point is the gamma point, here is this point x point. So, what I am plotting is 0 to 1 means it is basically value of alpha. This value of alpha I am plotting here, this says 0, 0.5 and 1, and this energy that I am plotting here is energy equal to, use the energy scale as energy divided by h square by 2m. This is the scaling I am using, nothing else, energy versus 2 pi by a whole squared. So, that is the energy I am plotting. Essentially, this is a constant factor. Remember, a is a constant and everything else there is a constant. So, this is just normalization of energy, nothing else. So, that is why I am able to use the word numbers like 1, 2, 3 here, etc., as dimensionless numbers right here because of this reason. So, I have made a dimensionless quantity. Other than that, there is no big deal about it. So, if I look at this, then that is what I am plotting. This energy which I have just mentioned to you, that is on the y axis. What I have done is, notice I am showing you this is an Excel file. In Excel file, I am using these different values of m1, m2, and here are the values of m1, m2 and m3. These m1, m2, m3 for different curves. I am going to show you here 8 different curves, where even m1, m2, m3 is equal to 0, 0, 0, here is 0, 0, 0, then m1 and m2 and m3 are equal to 0, minus 1 and 0, and m1, m2, m3 are 1, 1, 0, and so on. For these particular values 1, 2, 3, 4, I have shown 8 different sets of value. For each set of value, this set is indicated right here. 1 means this set here, 2 means this set here, 3 means this set here. So, I have 4 means this set right here, 0, 1, 1, etc. For these values, I have calculated energies, which you can see alpha is varying, I am varying from 0 to 1. Essentially, that means I am going from gamma to x is what I am going from there to there. And what happens then? So, x axis basically I am plotting alpha. So, energy therefore is accordingly normalized, and if I look at this point, this cell. So, what is the calculation I am doing? You can see right here that here is the value of alpha, alpha minus, look at the formula, m1 plus m2 plus m3 squared, m1 because it is a k squared now, and m1 minus m2 plus m3 squared, and then m1 plus m2 minus m3 squared. This is the square of it, and the in front is h square by 2m into 2 pi by a square. I have taken all that factor and divide energy, use that for division of energy. Therefore, only thing that is left is square of this part. So, I hope you understand this part. I hope you understand what I have just said. So, with this, now notice what happens. Here is the curve for this. If I calculate this formula, then here is the curve. This curve I have shown you here. This is for m1, m2, m3 equal to 0, 0, 0. Similarly, for these, well, in this case I have plotted 6 different curves from 1 to 6. You can ignore this 7 and 8 can be ignored. So, 2, 3, 4, 5, 6 curves I have plotted here, 1, 2, 3, 4, 5 and this 6 curve. For these 6 curves correspond to these different values which are shown here. All right. So, now we are going to do this. I am going to show you all the curves like this. Suppose so this we have plotted from gamma to x. Suppose you want to plot from x to w, which I am going to show you now next. So, let us do that also. So, this is gamma to x. Actually, let me write this out. So, if I want to calculate this so that there is no confusion, what I have done is I am going to write this as, if I take this factor, if I can write this as energy by h square by 2 m 2 pi by a whole squared. I can use this as equal to then square of basically this entire factor from here to here. Or let me use a different pen. Square of this factor only. Use this factor. Use this factor square of this red factor. Basically, dot product of this particular factor is essentially the square which I am plotting here. This factor is in here. This factor is in here. That's the square of it. So essentially, that's what I was telling you. I'm just plotting the square of this number, this dot product of this number, and I'm plotting this quantity versus alpha is what I am plotting to show you that gamma versus x. All right. Now, suppose you want to plot from, we went from gamma. So what we do is, the way we plot is we go in some major directions. So for example, we in this particular case, what I've just shown you is that we are going from gamma to x, which is a 1 0 0 direction. So we go from 1 0 0 direction, and then from x I am going to go to w. So from x I am going to go in this w, in this direction. So next plot that I want to make therefore is going from x to w. So if I do so, then let's go to next page here. Now I am saying that suppose we want to go to x to w, that means I want to plot similarly this energy versus h square by 2 m 2 pi by a whole squared is what I want to plot when my points vary from x to w. And remember, x point was equal to, let's do that, x point was equal to, remember, 2 pi by a x hat, and w point was equal to, remember, was equal to 2 pi by a x plus half y. So that was 2 pi by a x plus half y. So if I want to go from x point to w point, so if I again look at it this way, here is gamma right here, here is x, here is w, here is w point. I want to go from here to here. So if I want to do that, then let's see, let's just plot it out. So these 3 points form a plane. So here is gamma point, here is x point, and here is this w point, here is this gamma point, which is the reference 0 0 0, that's the origin, and here is w point. So what I want to do is I want to plot it as a function of this vector right here. I want to plot this k prime, this is the k prime being plotted from here to here, and this k prime I want to vary from this gamma point. So this is at this point right here, at this point, or let us use a color, at this point this vector is equal to this vector, this is vector at x point, k prime vector is this is the k prime vector, and at this point right here, which is corresponding to this point is this point, and k prime vector in that case this vector. So at any point in between, let's take this point, in any point in between, the k vector is k prime vector is this vector, and I am plotting basically k prime versus k prime vector is what I am plotting. So what is the k prime vector? Essentially we can write it down for x w. So I can write this k prime vector as, this k prime vector can simply then be written as equal to 1 minus alpha times gamma to x vector plus alpha times gamma to w vector. What does that mean? Let us use the black pen itself. If I want to plot this, essentially k vector, k prime vector means this. What does that mean? That means that if an alpha I will allow to again vary from 0 to 1. So what does that mean? That if alpha is equal to 0, then in that case I am essentially, my k prime is this vector, this orange vector or yellow vector, and that means it is we are an x point. When alpha is equal to 1, in that case I am really probing gamma to k vector is gamma w, and in that case this red point is the position here. So if I can now write down my k prime vector, so if I write down my k prime vector, therefore since I know what this, so as you can see, what is gamma to x vector? Gamma to x vector is of course 2 pi by a x, and gamma to w vector is what? 2 pi by a x hat plus half y hat is just this vector. So, this k prime vector now is equal to, simply I can write this as 1 minus alpha 2 pi by a x hat plus alpha 2 pi by a times x hat plus half y hat, which is equal to then 2 pi by a x hat plus alpha by 2 y hat. And therefore, I can now write k vector. This k vector then is equal to k prime plus k vector, and since k vector we already know, so therefore, we can add it up and you will get 2 pi by a 1 minus m 1 plus m 2 plus m 3 x hat, okay, plus alpha by 2 plus m 1 minus m 2 plus m 3 y hat plus m 1 plus m 2 minus m 3 z hat as this vector. So, now I can calculate for different values of m 1, m 2, m 3, the same way I can calculate this energy versus h square by 2 m 2 pi by a whole squared as essentially equal to dot product of this, again same, just this term within the brackets. Whatever this term in the brackets, I can take the square of it. So, this term in the bracket dot this term in the bracket, again I can do that part, and for different values of m 1, m 2 and m 3, I can now again plot this energy versus this curve. So, so let us do that again. Here is for x to w. So, this point is right here is x, this point is x, and this point is w, and again I have taken here 4 different values of m 1, m 2, m 3. This is set 1, set 2, set 3, set 4, and for this set 1, set 2, set 3, I can see here the formula here 1 minus m 1 plus m 2 plus m 3 squared, then alpha, this is the alpha in A 17 cell number of x cell, which is right here, this A 17 cell A, and this is 17 cell, this value divided by 2 plus m 1 minus m 2 plus m 3 squared, m 1 plus m 2 minus m 3 whole squared. Those are the values which are calculated here and plotted right here, and for these different 4 sets I have plotted this, and in principle I should be labeling this as 0 0 0, and I should be labeling all these values. Okay. The point is, now you can plot from x to w. So, if I do that, this is what I have done for from w to L. I have plotted from w to L, I have plotted from L to tau, I have plotted from tau to gamma, sorry, L to gamma, gamma to k, and k to x, and all these plots I have plotted, which I am going to show you now in one sheet. I will show them all to you together like this. Right here is then a band diagram for FCC, which you can now see that in this particular case, what do you see? So, here I had shown you a plot of gamma to x. So, remember, this is how it is varying from x axis, is varying only from gamma to x, and now I am using m 1, m 2. So, in principle, therefore, we are reading from any point, we can read here k prime vector. This is the k prime vector going from gamma to x. The real k vector then is obtained by adding capital K vector to it. And what is the capital K vector we are adding? The capital K vector we are adding is using this index of m 1, m 2 and m 3 as 0 0 0. Once we do that, then I can take the square of that to calculate the free electron energy. In any case, whatever the energy, corresponding energy is to that small k vector once from k prime. So, this is k prime is transformed to k by using these indexes which are written here for m 1 value, m 2 value and m 3 values. That means, it tells you what k has been used. This index tells you what k has been used to transform from k prime to k, and this axis must be read as k prime vector. So, you and k prime vector always belongs to first Boolean zone. So, you can confine that, and when I plot that, you can see this has been obtained by using this particular portion of the curve has been obtained by using this particular curve has been obtained by using any of these 4 values. this particular curve has been obtained by using any of these values, this particular curve has been used by using any of these values, and this particular curve has been used by obtained by any of by using this particular m1, m2, m3. Now remember, this happens only when I have chosen, for example, k point as or x point as 2 pi by a in x direction. I could have chosen it in minus x direction, I could have chosen it in y direction, I could have chosen it in z direction. So with that, new set of indexes will show up also, but very quickly if you see these directions m1, m2, m3, you should be able to see the degeneracy also. So these curves are degenerate curves, saying that different m1, m2 and m3 values are give you overlapping curves. That's showing you energy degeneracy. That's a separate issue which we won't be addressing in this class, but what have we, so this is plot, the way these band diagrams therefore are shown is by going from one major point in the 3D Brillouin zone, from one major point to another major point to another major point, major points of symmetry on this Brillouin zone. So for example, as we go from gamma point to x point to w point to L point, L back to gamma point, and from gamma point to k point and k point to x point, and this is how this whole band diagram has been constructed. And you can now see that for many different directions, all different major directions or different k points, we are able to represent this band diagram. All right, so I will make some observations about utility of these band diagrams in a minute, but similarly before I move on, let me also show this to you for BCC structure also. For BCC also, I've shown you that BCC B1, B2, B3 vectors start looking like this, then that means in reciprocal lattice it is FCC. So if I have shown you these FCC lattice points right here, these are the FCC lattice points, FCC lattice shown here, and if I again take the perpendicular bisectors, I have shown you the construction of the Brillouin zone. That Brillouin zone looks like this. Again, I have a gamma point right here in the center, then there is a point like this which is a H point. So there is a H point right here, this is the H point right here which I have labeled here also, which is equivalent H points. So these are, therefore this H has been labeled as 2 pi by x, but you are welcome to write it as 2 pi by a. You could have chosen H as 2 pi by a y, you could have chosen 2 pi by a z. This periodicity of course again is 4 pi by a. 4 pi by a is the lattice parameter of this unit cell. So 4 pi by a, so here's 2 pi by a x, you could have chosen H as 2 pi by a y, you could have chosen 2 pi by a z, whichever way, they are all equivalent points. Similarly, vector p or this point p is right here, whose coordinates are given here, you can verify yourself, and here is point n which you can verify here. Now again, for this structure also we can do the same exercise. We can do the same exercise for this particular case also, where we write down, go from one direction, from various directions, from gamma to h, h to p, p to n, and some place to gamma, write down the k prime vector. We can write down the k prime vector correspondingly, and to this k prime y vector we can add this k vector with using different m1, and remember m1 b1 plus m2 b2 plus m3 b3 is this essentially this k vector. So by using different m1, m2, m3 value, we can calculate k vector, and once I calculate the k vector, I can calculate the energies. Once I calculate the energies, I can do the same plot for BCC also. If we do so, then let me try to quickly show you before I end this lecture. If we do that, I have done that for BCC also, and for BCC I have plotted it from gamma point to h point, and it looks as shown here for different m1, m2, m3 values, same way. Then from h to p, I am moving very fast because now you understand how to do it, and you can consider this as an assignment problem for doing the BCC part yourself. Then p to gamma point, and then gamma to n point, and I am going to show all these together, and then from n to h points. So I have done this exercise in an Excel sheet myself. So I will ask you to do this for BCC, what I have done for FCC. I have shown you the details of how it is done for FCC. Exactly same thing has to be done for BCC, which you can try out, and let me show you how this will look like in that case, and you can compare it whether you get the same thing or not. So here is the curve. Again, I am plotting this E versus h square by 2m divided by 2 pi by a is whole squared versus this is the k prime vector. Here is the k prime vector that I am plotting here. This is the k prime vector going from gamma to h. Of course, you can think of this as k prime vector, or you can think of alpha going from 0 to 1. Either way, because the way we write it down is you use the parameterized form alpha. So, which is the trick I have shown you. So, this is the same. This is 0 0 0. I have written these indexes out. You can now what you should do is you should try out yourself the same exercise and plot this for BCC. This is for BCC. The previous one, of course, which I found was for FCC. So, this was FCC, and now this for BCC. I am not going to go over this, but gamma to h, h to p, p to gamma, gamma to n, n to h. And I will request you to plot this yourself. With this, you should be able to understand now. Now, let us take a minute or two to understand what have we done. What we have done is that we have understood now ultimately what we want to do. We want to show E versus K diagram. E versus K diagram is what we are calling as band diagram. We want to show that band diagram for real semiconductors in which are good for optoelectronics. Why do you want to do that? Not next lecture, but one after that. I will show you what information you can get from E versus K diagram. This E versus K diagram give us lot of information which is good for optoelectronics and electronics in general. So, those I will show you one lecture from this is in the 9th lecture. I will start telling you about that E versus K real E versus K diagram of semiconductors and what the utility of that is. So, in order to get to E versus K diagram, what we have done is there is one axis is E, other axis is K. We have figured out how to handle the K axis. We figured out K axis is a 3-dimensional axis. One second, its extent is infinite, minus infinite to plus infinite in all 3 directions. So, what we have done is we have learned how to handle in this lecture and the previous using the Bloss theorem. In this lecture, we have learned how to handle this x direction, this K direction, and represent it in this particular form as it's on your screen right now. So, this K, and we can confine this only within the first Brillouin zone. Once you have done that, then but the E axis, the energy axis is still a hypothetical energy values. That means, we have assumed as if the energies were free electron energies. Those in real systems are not the energy. In real systems, since there is a potential, the energy Schrodinger solution to Schrodinger equation must get modified, and that energy should be different. So, only thing left for me to do in the next lecture is to show to you that this energy will get modified. If we can calculate this energy again and a correct value, then instead of plotting the free energy value of energy we have plotted here, instead of taking k square and h square by 2m k square, instead of that, if I can for different k prime values which are shown on this axis right here, or k values or k prime values, whichever way you want to talk about, if I corresponding to that I can calculate the realistic energy, then I can show that realistic energy in here in this diagram which you see on the screen, and I will have my E versus K diagram. So, in next lecture I am going to show you first as an approximate case, I am going to show you what will be the consequence of periodic potential on energy. Previous lecture I have shown you consequence of periodic potential on the k axis. Now, next time I will show you the consequence of periodic potential on y axis, that is the energy axis, as an approximate calculation. Since real calculation is very tough, so I will show you only the and it's tough and also cannot be done in a closed form solutions, and then those require large programming, large software and huge run times, etc., and which I explained to you why that problem is complicated problem. So, what we are going to do is we are going to use the real calculations from literature and show it to you, but before that I will show you approximate calculation and show you what the consequence of periodic potential on the y axis, the energy axis will be, and from that point on, that will be 8th lecture. 9th lecture will be then, if we have a EK diagram, then what can we get out of it, what is the information I can get out of it, and in the 10th lecture then I will start showing you the realistic E versus K diagrams. Thank you.